Now let us see why we need this torsional reinforcement. As I said, when you twist a reinforced concrete element, I'm going to have the spiral crack, and that member is going to elongate. In addition to that, there's going to be a shear flow that is going to be going around the periphery of the cross section. So you will find these kind of cracking that will happen. Okay, so I need to put a reinforcement both everywhere in all the four faces. I need to put. So we put longitudinal rebar like this for both bending as well as torsion. In addition to that, we also put stirrups, and in addition to that, we also put some side face reinforcements. Okay, these are your side face reinforcements. These are your side face reinforcement. Okay, so this is for how we put in, because when we say that shear flow will have two components. One is the horizontal component, and one will be the vertical component. That is the reason shear is going to induce tension both in the longitudinal direction as well as in the transverse direction. So I need to put both the longitudinal bar as well as stirrups to account for this crack. Now let us see what happens just prior to cracking. Again, for a generic this kind of a section that I take, an L section, and then I'm going to say using thin wall tube theory how the shear flows would be. This is a closed section. So again, if you have a open section and closed section, let's say same section, if I create a slit, then you will find that that section will have very low strength and low stiffness compared to that of a closed section. So let's say this is total area of the section. We denote this as ACP. Now, if I convert this section into an equivalent thin tube, which a thickness of T, then you'll find the shear flow is going to go like this. Okay, because in the closed section, shear flow is going to go like this, and it is going to create a lot of each shear flow will create a. If I take about the center line, the lever arm for the shear flow is going to be quite high, and that's why the closed sections will offer much higher resistance to torsion, and the shear strength, torsion strength is also going to be quite high. And PCP is nothing but your perimeter of your section, and A naught is nothing but your area that is enclosed by this shear flow. Okay, because now what I have done, I've converted the solid section into an equivalent thin tube. Why is it? Because we know that the shear stresses are maximum around the periphery in a closed section. So it's a good idealization to simplify the calculations. Now, what is the thickness for a, I should assume for this thin tube? So, people have given this expression. You can take that as 3/4 of ACP by PCP. That means area of section divided by perimeter. You divide that them and then multiply by 3/4 to get the thickness. Now, how good is this? People have done some experiment and they have found that they are reasonably okay. Okay, so that is the reason. So once you do that, again area A naught that is enclosed within this thing also, we can take that as 2 times ACP by 3. So we know this solid area we know. So if I want the area within the thin tube, then I can take this as 2 into ACP by 3. And thickness can be assumed as 3/4 of ACP by PCP, which is your area of the section divided by perimeter of the section. Okay, right. Now, we have found that cracking torsional moment can be given as 2Q multiplied by A naught. So that's what we assume from a thin wall tube theory, right? So Q is your shear flow and A naught is your area enclosed within that thin tube. So again, in this case, what is the A naught? Again, if you go back, so I assume everything to be like a centerline tube, right? So what we are saying is whatever the area which is within the center line of this tube is nothing but your A naught. Okay, this is your A naught. Okay, area within that thin tube. So again, we know this. So what is Q? Q is nothing but tau into T. Now tau is T is this given by this, and tau if I keep it, so it will become 2 into tau into T, which is 3/4 of ACP by PCP multiplied by A naught, which is 2 into ACP by 3. So in this way, and again, shear stress can be always related as a fraction of your square root of your compressive strength. So if I take 0.33 square root of F prime C, where F prime C is your cylinder compressive strength of concrete, then And this is an assumption. So this is a maximum shear stress the concrete can take. So this is always maximum shear stress or maximum tensile strength is always expressed as a function of a square root of F prime. So if you substitute that, then you get a value for cracking torsional moment as 0.3 square root of F prime C multiplied by A square Cp by Pc. Or in other words, if I give you the concrete strength and if I give you the area of the cross section and perimeter of the cross section, you can plug into this equation, find out what is the cracking torsional moment of that particular section, right? So you can see that if I want to increase this, of course, I have to increase my overall area or increase the compressive strength. But increase in compressive strength will not give a major. If I want to improve your cracking torsional moment, the only way is to increase your A square Cp. In fact, in for torsion, providing wider beam will actually help. Okay, so now there is another theory. They said, okay, this is for calculating cracking torsional moment. You have used thin wall tube theory. After cracking, what happens? So after cracking, just like in shear we have done, it is converted into a two-dimensional truss. In torsion, after cracking, you go with all the spiral crack and so on, and then you have longitudinal bar and stirrup that are going to act as the tension elements. You are basically converting them into a three-dimensional space truss. So you can see here, this is what I'm going to have. So I'm having a longitudinal bar and I'm having stirrups like this. Okay, and in between them you have cracked concrete. So because the cracks are going to be spiral, so in between the cracks, diagonal cracks, concrete is going to contribute in compression, and the shear flow will be resisted through that concrete uh, uh, in 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 the direction. In addition to that, you are going to have longitudinal bar that is going to be in tension, and you will have again stirrups that are going to be in tension. So if you look at the shear flow, so this is your shear flow, and this is your angle alpha, the crack angle, and this is your Q. If you take this as a Q and perpendicular direction, I'm going to have Q by tan alpha, and similarly this direction you are going to have Q. So you'll find that uh, the perpendicular will be Q tan alpha. So if with this shear flow assumptions and with this uh, cracking assumptions of 45-degree, let's say it is going to make, then I can simplify and find out what is the amount of transverse reinforcement required and what is the amount of longitudinal reinforcement required to resist particular torsion. So let's see how to do that. Okay, so here in the space stress analogy, what we are assuming is the corner longitudinal bar will act as stringers which are going to be in tension, and closed stirrup legs will act as a tie member, and concrete between these diagonal cracks will act as compression diagonal. So you have tension element and compression elements. They are all connected together and to form a three-dimensional space truss. Okay, now let's look at it. How to get expressions for uh, amount of transverse reinforcement and amount of longitudinal reinforcement. So this we have calculated. Okay, so let's say I am. What is the thickness of the tube? We know how to calculate from a thin wall tube theory. And what is the shear flow? We know how to calculate shear flow for an applied torsional moment. Let's say TU. The Q can be calculated as TU divided by 2 into A naught. What is A naught? A naught is the area enclosed by the center line of this tube. So for example, in this case, let's say this is the center line of the tube, right? So what is the A naught? Again, A naught is the area enclosed within this. Okay? So that is A naught. So for a particular TU, and if I know the thickness of the tube, what I assume, so shear flow is nothing but TU divided by 2 into A naught. Now what is A naught? In this case, you can see that A naught is B1 into D1. So you can find an expression for shear flow for a particular torsional moment is Tu divided by 2 into B1 D1. So this is again. So this is the way the shear flow is acting Q. When this is there, this is going to be Q by tan alpha. And when this is Q, this is going to be Q by tan alpha. So we are going to invoke horizontal and transverse and longitudinal equilibrium to find out what is the expression for your longitudinal steel and transverse steel. Okay, now let's look at this. So this is what I said after cracking space stress analogy. So you have Q here in the vertical direction. So this horizontal component is going to be Q by tan alpha. Similarly, if you see here, this is Q and this is going to be your Q by tan alpha. Right? So if I look at the transverse equilibrium and the shear flow at any point when you look at it, let's say if I take a small unit length like this, okay, then whatever the Q that is acting in the vertical direction, the force will be Q into SV uh, multiplied by tan. Anyway, it is 45 degrees, so it will become Q into SV. So Q is anyway what? Shear flow. What is the unit for shear flow? It is basically kilonewton per meter or millimeter. When I multiply by spacing, I get my force, which spacing is going to be again in millimeter. Okay, let's say kilonewton. You are it. So you get force. Okay, so that is what we're going to get. So that vertical force is Q into S. That has to be resisted by only the transverse reinforcement. Now, what is the maximum force that transverse reinforcement can take? Area of that bar multiplied by the yield stress, which is 0.87 F. So, according to IS code, with the partial safety factor, the maximum stress it can take is 0.87 F. So, if I look at this element, okay, so the total force offered by this is 80 into 0.87 Fi. So this has to be resisted by Q into SV, which is the force. So that is what we are equating as the transverse force equilibrium. Then I can find an expression. Now I know what is the expression for my Q from your thin wall tube theory. What is Q? Q is nothing but Tu by 2 A naught, and which is nothing but Tu by 2 into B1 T1. So I go ahead and put that for Q. So it will become Tu into 2B1 D1 times SV will become 80 into 0.87 F1. Okay. Or in other words, I can relate the torsional moment that I'm designing to the transverse reinforcement in this form. Okay. Right. So if you give me Tu, I should be able to find what is At in this equation because I know what is B1 and what is D1, and I'm going to assume some stirrup spacing. I know what is the maximum stress that particular transverse reinforcement can take. So quickly I can find out what is the At that is required to resist this Tu. And this is one thing that you have to take into account. Okay. So for example, we have seen that when you have a shear, let's say these kind of cracks are going to come. Whether you look at it in the front side or back side, the same crack will be a through crack. I will be able to see from front side to the back side. So the crack is angular, crack is not going to change on all the planes. It is going to be a through crack. But in torsion, we have a spiraling crack. So usually for shear, what is it we have said? Okay, I'm going to put this kind of reinforcement, okay, which is going to arrest this through crack. And because this crack is same on the other side also, whatever we can either you can put a two-leg stirrup or a multi-leg stirrup, depending upon the number of legs of stirrup, all of them will contribute in the resistance, right? But in torch, we have a spiraling crack. Now the spiraling, and where is the maximum shear stress in torsion? Only on the outer periphery. If I go to the center of the cross section, my shear stress is zero. So only the outer legs in the cross section will be effective in torsion. Let's say most commonly we use a two-legged stirrup. So that is what we are saying. For two-legged stirrup, now only one leg of the stirrup will be effective in torsion because at any point of time only one leg is going to arrest the crack. But in shear it is not like that. If I'm putting two legs, all the two of them will resist the crack. So that is the reason for stirrup reinforcement for a two leg, we can take that as ASV is equal to 2 into 80. Okay. Now, right. So this is basically for every two leg that I am putting for stirrup for a shear, only one leg is going to be effective. So in other words, 2 times 80 should be provided for resisting the shear. Okay. So I can write ASV in terms of, so now 2 into 80 will become basically ASV. So I'm expressing in terms of vertical stirrup requirement for shear. Okay, so in this form I can write with a simple modification. Now if I invoke longitudinal equilibrium, now longitudinal equilibrium is what? Basically again the shear is going to resist my is going to create a longitudinal tension also. Let's see how is that longitudinal tension. So if you look at it, this is your component, which is basically nothing but Q by tan alpha, which is your component that is perpendicular to that cross section. Then when I multiply by the perimeter, that is the total tension force which is acting along the length of the member, that has to be resisted by the total longitudinal bar. The longitudinal bar has to be in tension. So AL multiplied by 0.87 Fy. Let's say AL is a total longitudinal bar. That can be over the entire perimeter also. Okay. So AL times 0.87 Fy is total longitudinal tension that is developed in the member. That has to be equated by the 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 out of plane component of the shear flow, which is Q by tan 45, multiplied by the perimeter, will give me the total force that are acting in the perpendicular to the cross section in the longitudinal direction. So that longitudinal equilibrium that we are equating. Then what is that I'm interested is I'm relating TU to A. Okay. Now we know what is the expression for Q, which is TU by 2 B1 D1. So again, if you substitute that, you can find an expression for your TU and A. Now AL in this case is entire longitudinal bar, both at the top, both at the top and bottom, and whatever that is there on the side also. Now what I have to do is from equivalent flexural capacity, if I want to convert this into an equivalent flexural capacity, though the total longitudinal bar is AL, I am going to assume that only whatever that is on the tension side is going to contribute in flexural resistance, right? So AL by 2 is the total amount of bar that is going to contribute in flexural resistance. So, and we know that for an under reinforced section, my lever arm is going to be, Z is going to be very close to that of your effective depth, right? For an under reinforced section, if you go back to a moment curvature analysis, we said 50 mm, 55 mm for a 600 mm. So you will find that the lever arm will be nearly equal to that of your effective depth. So I'm going to take AL by 2 is the area of bars, longitudinal bar that help me in bending resistance. AL by 2 multiplied by 0.87 Fy is nothing but your TS multiplied by lever arm, which I am taking it as D or D1. So that is nothing but your MT, which is your equivalent bending capacity for the torsion. So my idea is torsion, I want to convert them into an equivalent bending moment. Again, torsion, I want to convert them into an equivalent shear. Then calculate the reinforcement requirement. Then I'm going to add it to what I have already designed for flexure and shear. So in this way, AL by 2 will be your AL by 2 multiplied by 0.87 Fy will be your tension contribution, and multiplied by lever arm will give your equivalent. So we are converting the torsion into equivalent bending moment. So that's why we are doing this exercise. So if I substitute AL by this equivalent as MT in this equation, then you will find that MT will be nothing but TU times B1 plus D1 divided by 1.7. Okay, so this is an expression for a particular torsional moment. I can convert them into an equivalent bending moment like this. Okay, so what is the assumption? Again, AL, what we have done from a longitudinal force equilibrium, only half of them are assumed to be contributing it in flexion, which is a reasonably good assumption because whatever that is on the tension side is only is going to contribute in bending. Okay, there is another theory that was proposed, which is called as a skew bending theory. Okay, so for a cross section that is subjected to both torsion as well as bending, and you can convert them into an equivalent resultant vector, moment vector, and depending upon whether you have very low torsion and high bending or very high torsion and low bending, the direction of this resultant vector is going to change, right? Now you can have several scenarios. Okay, when you have very low level of torsion and significant amount of bending, then what will happen is torsion is going to modify the bending. Now your if you look at the surface, it's not going to be perpendicular. You're going to have a skewed surface. So the presence of torsion is going to skew the failure surface, and it is going to create. However, you will still have compression at the top, okay, and tension at the bottom. So this type of failure mode is called as modified bending failure, where you have some limited amount of torsion along with high bending moment. So it's not going to completely change the failure mode. It's going to slightly modify the failure mode. Still, you're going to have compression at the top and tension at the bottom. Now let's look at this third failure mode. If and we have seen torsion, what is that I said? The moment you have spiraling cracking, the entire length of the member is going to extend, right? It's going to elongate that member. So torsion is going to produce, like we have seen in the shear flow. Shear flow has both components, horizontal, vertical component. We say that shear flow is going to create tension around the periphery of the cross section. So torsion is going to create tension everywhere. Okay, but bending, what does it do? It is creating tension only on one side, right? One side compression, one side tension. So you can see that the torsion is creating tension around the periphery of the cross section. However, bending is creating tension only at the bottom. So I can have a situation when you have torsional moment is very, very large and bending is very small, then what it can happen? That my tension due to torsion will be very high around the periphery of the member. However, tension due to bending will be only on one side. Now I can have a situation that tension from torsion can nullify the compression that is coming from bending, and it can also create tension at the top as well. Okay, so that is what we are saying, that as negative bending failure mode. This will happen when your torsion is very, very large compared to that of bending, and this will happen when your bending is very, very large compared to that of torsion. Okay, so this mode 1 and mode 3 are very different. So now what is it we are saying? When you have very torsion, now I am going to create tension at the top also, which we don't account for. So when you have a torsion, when it is very, very large to bending, bending will create compression at the top. That's our assumption. And then depending upon let's say it's creating a sagging mode. So it's going to create compression at the top and tension at the bottom. Now, when you have a torsion which is much, much larger than bending, what will happen? Top also you'll have tension. So that I have to account for them in my design. That is what the code is going to say, ME1 and ME2, which we will talk about that. Now this is mode 3 failure. So in fact, some of our provisions are from skew bending theory. Now you have mode 2 failure also is possible when your members are very slender, or in other words, height to breadth ratios when it is very large, you end up with slender members. Then you have both T and M, or let's say substantial. Okay, in that case, and also when you have a member which is deeper with less breadth, then you have end up with this kind of a lateral bending scenario where your compression zone will be on the side and similarly tension zone will be on the side. So this is similar to having lateral bending kind of failure. This will happen when your members are having very large depth to width ratios. Okay, when the members are slender, when it is prone to lateral bending, you will in that kind of scenario both torsion and bending would be significant. Now, depending upon, just like we can draw the interaction curve between axial compression and bending. People have done some experiment, and based on the skew bending theory, assuming different modes are going to govern, people have come up with these kind of failure curves. Okay, so what you find here, these are nothing but your failure curves. You do your design, and what is there on the y-axis? Tu by tur. That means Tu is your demand, and Tu is your demand. Okay, and tur is your resistance. Okay, similarly, mu is your demand. Mur is your resistance in bending, in pure bending. And TUR is a resistance in pure torsion, MUR is a resistance in pure bending, right? Depending upon the amount of compression steel to the tension steel, you can have these kind of different failure curves can happen. So that I can calculate these resistances based on the skewed failure surface that I am going to assume. Okay. For mode 1, we know that it's a modified bending failure mode, and you find that you have, for when your AS prime by AS is this, then mode 1 can take 3 different types of curves. And mode 3 can happen when you have this. Okay. When your bending is very, very small compared to that of torsion, then you can get up this kind of a failure, which is a mode 3 failure. So modified bending failure mode. So this is the curve expression, and Tu is your torsional demand, TUR is your pure torsional resistance, Mu is your flexure demand, and MUR is your pure flexure resistance. So That again, it is also function of how much is the distribution of compression steel to tension steel. And mode 1 likely to occur initiated by yielding in tension steel, and this becomes inevitable when AS prime equal to AS. The reason is section becomes doubly reinforced and you have reinforcement on all sides, so you will end up having an under reinforced or failure initiated by yielding of tension. So then you can also have a negative bending failure mode that we have talked about, which is a mode 3. When your torsion is very high compared to that of bending, you can have this kind of a failure mode. This can occur by initiated by yielding of compression steel when TU exceeds pure torsion strength in the presence of bending moment. Why this TU is exceeding pure torsion strength? Now, bending is going to create compression at the top that is going to relieve the tension that is created by torsion. So, that is the reason in this case your strength is increasing up to a certain limit. Okay, just like in you have a pure axial compression bending, here the presence of bending will help to an extent to relieve the tension that is created by torsion. Okay, so this is the mode 3 failure. Anyway, in our code IS 456, we don't really worry about what are the failure modes that are going to happen. We are just going to convert the torsion from your analysis into equivalent bending and equivalent shear, and you're going to design like what you designed for flexure and shear. Okay. Anyway, this you should be aware of. The failure modes can change depending upon the relative magnitudes of your bending and torsion. So similarly, I can find out the interaction between shear and torsion. Okay, so this is what I am having it in the x-axis. We use the shear demand divided by pure shear resistance. Now again, pure shear resistance. You know how to calculate the shear capacities, which we have discussed in the previous module. Similarly, for torsion. So if I do that, you can have different failure curves that are possible. These are all failure curves depending upon what is an alpha. Okay, alpha is purely a function of okay strength of the members in flexion. So you can take, in fact, alpha generally we take between 1 and 2. That depends upon the amount of steel that you're assuming. So this way I can also derive an interaction between the shear that is existing in the cross section versus torsion that is existing in the cross section. Okay, and yeah. So this is the overview. So in this module, we talked about torsion. What is torsion? What are the two types of torsion? Equilibrium torsion and compatibility torsion. And how shear stresses are developing in torsion in solid and hollow sections. And how to estimate torsion rigidity. And how the behavior of torque versus twist in a plain cement concrete beams and RCC. And we also saw putting a lot of steel also is not going to really help in increasing the ultimate strength of torsion. It will help to an extent to arrest the crack width and uh, performance of the beam, but strength is not going to increase much. And we also talked about how to calculate cracking torsion moment using plasticity theory, and then how to design a concrete section with the reinforcement using space stress analogy and skew bending theory. Our IS 456, most of the provisions are from skew bending theory. However, space stress, other codes like Euro code or American code, they have switched to space stress analogy. They are using extensively the space stress analogy. In this module, we discussed how space stress analogy is a very elegant way of uh, representing the torsional behavior. And we also talked about what are the influence of torsion, shear, and flexure, and when it is combinedly acting, how the failure curves are going to change, right? So these are some of the references, and thank you. And in fact, the slides were prepared by one of my PhD student, Mr. Mutturaja. I would like to thank him for all the help that he gave in presenting and preparing this lecture notes. Thank you.